What if a billion-dollar mistake ended up changing everything we know about the universe? The Hubble Space Telescope. We know it for the galaxies it has captured millions of light years away, and for the countless nebulae filled with newborn stars. Since its launch in 1990, Hubble has carried out nearly 2 million observations, from iconic images like the Eagle Nebula and the Pillars of Creation, to the deepest views of the universe ever taken. These observations have been so groundbreaking that they've contributed to more than 22,000 scientific papers. But Hubble's story didn't begin with images like these. It began with one of the most expensive and tragically ironic mistakes in the history of astronomy. The conclusion we've come to is that a significant spherical aberration appears to be present in the optics. Earth's atmosphere is the reason stars seem to twinkle in the night sky, and a complete nightmare for astronomers. That twinkling means the light traveling from the universe is being distorted as it passes through layers of air. That's why the idea of placing a telescope beyond Earth's atmosphere is much older than most people think. Long before space travel was even imaginable, German rocket scientist Hermann Oberth already understood there was only one way to solve this problem. In 1923, decades before the first satellite was ever launched, Oberth proposed the concept of a space-based telescope in his book, The Rocket into Interplanetary Space. But turning that vision into reality would take many more decades. The technology of the time simply wasn't advanced enough to catch up with his ideas. In 1946, American astrophysicist Lyman Spitzer put forward a realistic and detailed plan for a space telescope. But making it a reality wasn't just an engineering challenge. It was also a test of patience. Spitzer spent nearly 30 years persuading both the scientific community and the government to get behind it. By the 1970s, NASA and the European Space Agency finally joined forces to bring this massive idea to life. The goal was clear from the start: a precision space telescope with a 3-meter primary mirror. When funding officially began in 1977, the telescope already had a name: Edwin Hubble, the astronomer whose discovery of the expanding universe had reshaped modern cosmology. During construction, however, budget constraints forced a critical compromise. The primary mirror was reduced from 3 meters to 2.4 meters. The size was smaller, but expectations remained sky-high. The astronomy community waited with great anticipation for this new space telescope, a machine believed to unlock the deepest secrets of the universe. But no one knew what was coming. After nearly 70 years of dreaming, after the work of hundreds of engineers and scientists, and after a $1.5 billion project, Hubble finally sent its first images back to Earth. This was the result. No one could have imagined something this bad. As you can see in these images, Hubble was unable to focus properly. A billion-dollar space telescope that simply wasn't working as intended. Like all professional telescopes, the Hubble Space Telescope is a reflecting telescope. It uses a large mirror to collect and focus light from distant objects. That primary mirror is 2.4 meters across and weighs 828 kilograms. Thanks to its Cassegrain design, Hubble is lighter and more compact than most telescopes of a similar size, which made it ideal for launch into space. When we say Hubble is a reflecting telescope, we're not talking about a simple mirror. Even in amateur reflecting telescopes, the mirror surface is polished with extreme precision, down to a fraction of a wavelength of light. The imperfections on that surface are often smaller than 1,000th the thickness of a human hair. Hubble's primary mirror represented the absolute limit of industrial and scientific precision at the time. It had to be the smoothest, most accurate surface ever produced. To achieve this, the 2.4-meter mirror was polished for months to an unprecedented level of smoothness. To put that into perspective, if we scaled Hubble's mirror up to the size of the Earth, the highest peak or deepest valley on its surface would rise only a few centimeters. But for Hubble, even that wasn't enough. The mirror's curvature had to bring all incoming light to a single focal point. To verify this, engineers relied on a specialized measuring device called a null corrector, essentially a reference tool that checked whether the mirror had reached its exact intended curvature. This is where the real problem was. Inside the null corrector, a single lens had been positioned just 1.3 millimeters off. It had been installed incorrectly. As a result, the device was giving false feedback, telling engineers that the edges of the mirror needed just a little more polishing. Unaware of the error, the engineers did exactly what any rational team would do. They trusted the instrument and shaped the mirror accordingly. The total error was just 2.2 microns. About 1/50th the thickness of a human hair. But that was enough. Hubble's primary mirror was supposed to bring all incoming light to a single point on the secondary mirror. Because the outer edge of the mirror was ever so slightly too flat, the light hitting that edge was reflected to the wrong focus. Instead of converging at one point, the image spread out. And that is why Hubble's photos appeared blurred. In astronomy, this type of optical error is called spherical aberration. So when we say the Hubble Space Telescope was nearsighted, we're not stretching an analogy. A very similar problem occurs in the human eye. If the shape of the lens or cornea isn't perfectly regular, light entering the eye focuses at multiple points, resulting in blurred vision. As humans, we solve this easily with glasses or contact lenses. And in fact, NASA decided to do exactly the same thing for Hubble. The Hubble Space Telescope needed glasses. The problem was that Hubble was no longer on Earth. It was already in space, orbiting 547 kilometers above the surface, moving at 27,000 kilometers per hour. NASA had two options. One was to accept this $1.5 billion telescope as one of the most expensive mistakes in history. The other was to do something no one had ever done before: to repair a space telescope while it was still in space. We have a go for main engine start. 5, 4, 3, 2, 1, go. And we have liftoff. Liftoff of Space Shuttle Endeavour on an ambitious mission to service the Hubble Space Telescope. In 1993, NASA launched the Space Shuttle mission known as STS-61. It was, in every sense, a rescue operation. The 7 astronauts chosen for the mission spent months training on full-scale replicas of Hubble inside massive underwater tanks, rehearsing every movement and every bolt over and over again. On December 2nd, 1993, Space Shuttle Endeavour launched to save Hubble. Of course, the astronauts couldn't replace Hubble's primary mirror in space. The telescope's complex design made that impossible. But that same complexity also offered more than one possible solution. Although the problem was in the mirror itself, Hubble didn't rely on a single optical element. It was equipped with cameras and scientific instruments designed to capture the light collected by the primary mirror. The most important of these was WFPC-1, the Wide Field and Planetary Camera, often described as the telescope's main eye. But this camera had been designed to work with a perfect mirror. Once the mirror turned out to be flawed, WFPC-1 could no longer do its job. That 2.2 micron error had effectively blinded it. So the astronauts removed WFPC-1 and replaced it with WFPC-2, a new camera specifically engineered to compensate for the mirror's flaw by correcting light in the opposite direction. But WFPC-2 wasn't the only instrument aboard Hubble. The telescope also relied on spectrographs and specialized cameras to analyze light across different wavelengths. Without fixing those two, Hubble could never reach its full potential. That's why NASA engineers developed a system called CoStar, an optical correction unit roughly the size of a refrigerator. Inside it were multiple small mirrors, 5 pairs of corrective mirrors mounted on deployable arms. Some of these mirrors were smaller than a coin, yet once installed inside the telescope, they functioned like tiny eyeglass lenses, bending the incoming light back into focus. The STS-61 mission lasted 11 days in total and involved 5 spacewalks, each between 6 and 8 hours long. Alongside WFPC-2 and CoStar, Hubble's solar panels, gyroscopes, and several electronic systems were also serviced. The mission cost NASA more than $600 million. But when it was over, Hubble had an entirely new view of the universe. To test the repair, engineers chose a comparison target, the Messier 100 galaxy, located 55 million light-years away. The before and after images made one thing unmistakably clear: Hubble's vision problem had been fixed. The Messier 100 galaxy had only been selected as a post-repair test target. But about 16 months after the servicing mission, on April 1, 1995, Hubble was pointed toward the Eagle Nebula. There, it captured one of the most iconic images in the history of astronomy: the Pillars of Creation. Before Hubble, Earth's atmosphere had prevented us from seeing nebulae with this level of clarity. But in this image, the towering pillar-like structures formed by cold hydrogen gas and dust were revealed in breathtaking detail. Although they appeared cold and lifeless, Hubble allowed us to clearly see regions filled with the raw material from which new stars would eventually be born. Launched with a mirror that couldn't focus properly, Hubble had now proven itself to be one of the most powerful scientific instruments ever built.